So to assemble the beam expander, first we have to align the objective and the spatial filter. In the pre-lab, we used the microscope objective with a numerical aperture of 0.25, and we calculated and found out that the size of the spatial filter has to be 23.6 microns. So in the setup, we continued to use the objective with the same numerical aperture, and we use a spatial filter of 25 micron in diameter, as that is the only one available and closest to the calculated value. So the spatial filter mount has 3 degrees of freedom, X and Y on the spatial filter and Z on the objective. So the trick to align the spatial filter is to move the objective away from the spatial filter first. Then you control the X and Y translation, so you can get the maximum intensity of the beam out. And then you slowly move the objective toward the spatial filter. And then you repeat the same procedure until you get a clean laser beam with no fringes around on the screen. So essentially the spatial filter is to focus the beam and block most of the noise. And because the pinhole we picked is 25 microns in size, which is slightly larger than the calculated value, so we expected some random fluctuations on the intensity profile of the laser beam.
After aligning the spatial filter, we went in to add the collimator. In pre-lab, we calculated that we needed a 175mm focal length lens for our beam expander. That was not available, so we used a 250mm focal length lens. This means that the beam size coming out of our expander would be larger than we expected, which should produce a smaller spot size in the end. To do the rough collimation, we slid the collimator along the axis and looked for a point that the beam did not diverge or converge at any point. And then to do the fine tuning of our collimation, we placed a shear plate in the beam path and adjusted the position along the optical rail again until we got fringes that lined up with the reference line in the shear plate. As you can see, when the beam is collimated, you get straight fringes along with the reference line. If it is not collimated, you will get slants in the lines in either direction.
So now that we have our Keplerian beam expander, we have a collimated beam coming out of the end. But this is too large to focus onto our photodetector, so we have a 250mm positive focal length lens to image that down onto the photodetector. And we have our knife edge that we were able to move in 10 micron increments across the X direction. And we were able to get our Gaussian beam distribution for these. So moving the knife edge across the the X position gives us our power output varying for the amount of power from the laser, and this gives us our Gaussian beam profile. So here are our 2 positions for our knife edge and photodetector, showing our Gaussian beam profiles.
The beam waste that we measured was 7.1 microns. The theoretical value for the beam waste using the values for the lenses that we used was about 7.86 microns. This was about 9.67% error on our measurements.